So I see this slide deck on my Teams.
Yes, we can see that, Hans.
Yeah, I can see them in the US.
Awesome. If they can see it in the US, I think then everybody should see it. No? And hi, Alex. Thank you so much for joining us this early. Very good.
You're very welcome.
So I'll continue. I mean, if it's going. Excuse me. Okay, then with this, I hope that all the practicalities should. Yeah, it's a challenge. I mean, it's we would have loved to do this, of course, in person, but I think with some small issues in the beginning, if we get those out of the way, we should be able to do it virtually as well. All right. So we start off with a short setting the scene. I mean, it's going to be a bit setting the scene on what petroleum substances are, a bit on refining, some high level on the analytics, and then introducing the challenges. I'll take the first part of that, and then I'm going to give the floor to Carol Benner, our Science Executive for Safety and Reach. And Carol is also leading our extensive analytical program, of which you will hear get an overview today in the different presentations, actually, but starting with this one. But we'll start with a bit of background on petroleum refining. I mean, I'm the first one to admit that there will be a lot of people on the line with way more experience and expertise on petroleum refining than I have. But there is also going to be some people who are probably less familiar with it. And I think we want to start with the same basic level of refining. So we'll give you the Petroleum Refining 101 to start for. Yes, okay. So petroleum substances, it all starts with boiling crude oil. The light molecules boil off first. So if you at lower boiling temperatures, you get shorter chain molecules, lower molecular weight, and it starts off with feedstocks that go into chemical production, and then you get your light petroleum streams, things like gasolines, diesels that we put in the car, kerosenes, and into the heavy fuel oils that basically are getting into products like marine fuels. If you then process it further under vacuum, so the molecules that we cannot distill under atmospheric conditions, we can then on the vacuum process further, and you get the heavier substances like bitumens, lubricant base oils, etc. So in this way, we make 166 petroleum substances. These substances typically contain hundreds to millions of, literally millions of molecules, and these molecules are made up of hydrogen and carbon, of course. So we have hydrocarbon molecules in these substances. And that makes these substances quite complex. So the substances are what we call archetypical UVCB, so prototypical UVCB substances. And these substances are, for a part, unknown. I mean, if you have millions of molecules, you can imagine you cannot know them all or identify them all. They are variable in nature. So if I take a sample today, it will be different than when I take a sample next week or maybe even tomorrow. Complex products and of course of biological origin. We have almost 4,500 registrations for those substances in our for REACH dossiers. And these dossiers are updated on a yearly basis with a comprehensive dossier update. So all the work that we do throughout the years in terms of scientific work or regulatory-based work is all finding its way into the dossiers. We do that already since the early registrations in 2010, and we have an annual process to follow there, which keeps our dossiers up to high standards with the current state of science. All the data is then used under CLP to classify and label our substances, and I've put a reference there to our labeling report that we publish, keep up to date as well, and we publish online on our Concawe website. Worthwhile to have a look at that. It is a nice summary of all the different petroleum substances and their classification and labeling, and it is a nice summary of all the data that go behind that with references to the data. Petroleum substances are a high volume on the EU market, but I think it's important to understand that regarding non-fuel widespread uses, so for consumer and professional exposures mainly, it's only about 2% of the total volume. everything that's non-fuel that way. So let's dive deeper a little bit into the concept of UVCBs, and in particular the first two aspects of UVCBs, the unknown and the variable. So as I said, in terms of the unknown, of course, if you have a large number of constituents, up to millions literally, or even more, it is impossible to identify them all individually. So petroleum substances are, as we state there, the constituents are collectively analyzed. So instead of, well, we can target individual molecules, and we'll get to that later in the presentation as well. So where we know we have certain, for example, health or environmental issues, we can target these molecules. But when we look at chemical composition and all of that, we collectively identify these constituents. But as you can see on the right side in the figure, when you go up in boiling point, so that's the refining diagram that I just showed, that the complexity increases very quickly. So in the heavy molecules, we have a lot of molecules there, and this is only the alkanes. There will be many more in real life. So then in terms of variability, indeed, petroleum substances are variable in nature, but the variability is of course limited because all these substances have to meet product specifications. I mean, we always joke a little bit that you cannot burn a bitumen in a plane. You cannot fly a plane on bitumen, but it is a bit like that. All the substances need to be made according to specifications so that variability is contained. And you can see that in the diagram there. So if you have a boiling point curve for a certain substances similar to that, so in one group of substances will have very similar boiling point curves, and the variation is really limited within the specification of those products. Petroleum substances also form a continuum. So it's not that we, in the diagram I just showed, that we have very clear cuts. Going from one stream to another, there will be overlap. So the heavy end of the first stream will overlap with the light end of the next stream. So there's always a window of overlap. And in this way, all the substances form a continuum. And I think these aspects are quite important if you talk about things like variability and so on in your assessment. There is if you look at the substances in a more holistic fashion, there are ways probably to address that. And these are concepts that we take along in the presentation when we go more into more detail on our assessments and the challenges that we are facing. So if we keep these things in mind, if we then look back at the refining diagram and now in a little bit more detail, you see here an overview of examples of refinery processes. And I mean, just to note that a typical refinery will not have all of these processes on one side, of course. But this is just to give you an impression of the different ways, the different manufacturing processes that can produce these petroleum substances. And what you see, what is important to take home here is that there will be different manufacturing processes which can produce very similar substances. So, for example, there are different ways of making a diesel product or a kerosene or so. And in this way, based on manufacturing processes, if you manufacture or produce those substances, you will get groupings of those substances already. And our Concawe categories are actually made based on those groupings. So what you see on the right side are the categories of substances we use in Concawe for REACH registrations. And you can see that kerosene are grouped together, gasolines are grouped together, bitumens, etc. So you have these logical groupings, actually, these logical categories. But we also know, because of this, that if you look at the physical chemistry of manufacturing, refining crude oils and manufacturing these substances, we know that within these groups, then the chemical composition is similar between those substances in a group. So if we know that, if we look at, take the physical chemical properties of boiling crude oil, then we know that the constituent profiles, so the analytical chemistry of the substances within within one group of substances, even though they are produced by different manufacturing processes, they will still be very similar within that group. The substances within that group will be very similar. So they can have different CAS numbers, different substances, but they will be similar in composition. And if we know that, then if you know that there's a link between the analytical chemistry and the toxicological hazards, so the health and environmental hazards, then you would expect that actually within such a group that these aspects, these toxicological, so environmental and health hazards are also similar within a Concawe category. Of course, this is still all very theoretical. We need to have a strong data set to support all of this, and that's analytical data, compositional, but also more detailed analytical data to support our hazard assessments, and then a lot of hazard data. So we'll give you a high-level overview of those, and we'll first start with the analytical data with Carol. So I'll give the word to Carol now.
Yep, thanks, Hans. So the analytical characterization of petroleum substances can be broadly described in two programs addressing registration and evaluation. And both of these are supported by the Substance Identity Management Group here in Concawe. To the left, the program supports registrants in the selection of the correct substance identity for registration and thereby joining the correct joint submission. This is a very important precursor to hazard assessment. Based on collated registrant data, Concawe has developed a substance identity profile for each petroleum substance, describing source, manufacturing process, and indeed the boundary compositions for each measured constituent for each petroleum substance. These measurements are based on industry standard methods that provide a high level of information about the substance constituents. For example, we have simulated distillation gas chromatography, which measures boiling points and therefore carbon number. We have liquid column chromatography, LCC, that measures grouped constituents as saturates, aromatics, and polars, and high performance liquid chromatography, HPLC, that measures again total monoaromatic, diaromatic, and tri-plus aromatic constituents. So Concawe has provided guidance to registrants on the selection of the appropriate industry method, analytical method for each substance category. Once correctly registered, we can then focus our analytical support on the hazard assessment, both for human health and the environment, and that we see in the right panel. And here we need far more granular data about the substance constituents. And for this, we use a wider range of non-standard methods, including gas chromatography, mass spectrometry, and two-dimensional gas chromatography. These can measure either specified constituents or hydrocarbon classes globally, or indeed by carbon number. For this, indeed, we need multiple samples per substance to be able to understand the variability in composition. And of course, analysis in a single lab per analytical method allows us to provide a consistent data set so that we can facilitate a comparison between data across all the samples. Such program data is included in our dossiers, or will soon be included in our dossiers, and it's also managed in a Concawe analytical database and allows us to inform both the human health and environmental hazard assessment programs. So an analytical characterization of each of the Concawe petroleum substances has been published last year, and you see the details referenced at the foot of this slide. So how far can we go analytically in characterizing petroleum substances? The granularity in quantifying petroleum substance constituents is influenced heavily by carbon number, the volatility of the substance. As carbon number increases, then the number of constituents increases exponentially. There are 200 to 300 constituents in a low boiling point naphtha, and each of those can be quantified, whereas there are many millions of constituents in a residual aromatic extract, for example, and these cannot be individually quantified or even identified. As carbon number increases, so do the molecular weight of the constituents and the diversity of the chemical functionalities. Lower boiling point substances have a simpler set of functionalities, including a single functionality per constituent, like the monoaromatics, whereas higher boiling point substances have multiple constituents, and each of these constituents can have multiple chemical functionalities. So with this increasing complexity, with the comprehensive identification and quantitation of petroleum substance constituents decreases as we increase the carbon number. Of course, specified constituents can be quantified across the full hydrocarbon range using mass spectrometric methods. However, the number of these constituents that can be measured in this way remains very low in comparison with the millions of constituents present at high carbon number. This approach of specified constituents has been taken to assess levels of substances of very high concern and those constituents that are believed to drive toxicity. For example, benzene and the 3+ ring polycyclic aromatic carbon constituents. It's these constituents that are very well studied. And with that, I hand back to Hans.
Thanks, Carol. So indeed, and I've referred earlier to the classification and labeling report, and some of that is summarized there. So the in some cases, constituents drive the drive the hazard effects of our substances, and this will be described in that report. But we of course have a lot more data than only that. This is just a very quick overview. It's just used for illustration. Don't really look at the detail, but it's just to show that over the last 50 years or so, a lot has been published in terms of toxicity assessment, both human health and environment, on petroleum substances. And some of that, of course, has been generated under different regulatory schemes. So, for example, under the Dangerous Substances Directive here in Europe, but also in the US under the High Production Volume Program, the HPV program. There's quite a lot of work being done. And all of these data, the relevant data, has found its way into our dossiers. So our dossiers back for 2010 registrations, and leading up to there, when we were building our dossiers, those data have found its way in there. So some of our dossiers contain a high number of study reports. So that ranges from physical chemistry, analytical reports to mammalian and ecotox studies and data. So these are summarized in Euclid and our CSRs, of course. So the hazards and the risks of exposure to our substances are managed based on those data, again, as summarized in our CNL report. But we know that there are still data gaps, and we know that there's a need to further support the existing data set with new data. So what we need to do is to find a pragmatic way of doing this, because we have 166 substances with a whole lot of endpoints, and for a number of reasons, including animal welfare and others, time to generate the data, it's probably undesirable to start testing them all. So we need to find a pragmatic way to really make best use of the existing data that we have, generate new data, and provide the necessary information to support the approaches to be able to make best use of these data. Now there is guidance, of course, in the legislation on how to do this, and there is guidance, for example, around grouping and read across, which is the main alternative method proposed in the regulation. But you can imagine that with complex substances, as we have presented now, this is not very straightforward. If you have to build your grouping and read across assessment on structural information, so structural similarity needs to be demonstrated in order to support your read across. That's fairly straightforward with a well-defined chemical, but with a substance containing hundreds to millions of constituents, that's not so straightforward anymore. So we need smart solutions there, and I think that that is also acknowledged in the read across assessment framework. That for UVCBs, it's not impossible, but it's more work and more data, more information is needed there. And hopefully today we can touch on some aspects of that. We can present some of the work that we have been doing in this, and hopefully agree together that this is a step, maybe even a small step, but a step in the right direction, and hopefully can have a good open discussion on the work that we have done so far to try and address these challenges and learn from the feedback today in order to prioritize and optimize our strategy and our work programs going forward. So in summary, we've seen that petroleum substances contain a lot of constituents, which, if you end up in the heavier streams with millions of constituents, they cannot be characterized individually, to the individual level. So you have to be collectively characterized. They are variable in composition, but that variability is contained within the product specifications. They form a continuum, so there are not clear cuts between going from one category to another, or even between substances. There's an overlap, and they are grouped into categories which are sort of logical groupings based on the manufacturing processes that we've seen in the beginning. Within these categories, the analytical chemistry of the substances within a category is the same, is similar, not the same, but is similar, due to the physical chemical properties of refining crude oil and the manufacturing processes leading to these substances. And if you know that, then the biological response of these substances is thought to be similar as well. But we know that we need to generate more data, and then we are generating the data to support these claims. And we know, despite the fact that we already have quite some data, we also need to generate more data to support the existing data set and to support filling the data gaps with a pragmatic testing strategy going forward. So with that, I want to introduce the two challenges, and I think it should be clear going from here what these are. So we have two. The first one is around the human health assessments. As we said, it is probably, well, it is undesirable to start testing them all. So we have to see how we can find a pragmatic way to target the animal testing and support read across of information to the ones that we don't test with thorough data, meeting the regulatory requirements, which helps to address issues like animal welfare, but also time to compliance, because testing them all is going to take, well, decades to test everything. And with a pragmatic testing strategy going forward, we can reduce that time to generate the required information. The second challenge will be quite similar, but then on the environmental side. And I'm saying similar, but it's, where the health challenge is more on this substance level, the environmental challenge is going to be more on the constituent level and on the block level. So how do you make sure that we don't underestimate impacts of petroleum substances on the environment, keeping in mind that we cannot test and cannot assess all of the constituents in a UVCB substance. So how to overcome those practical challenges in that area. So we'll dive into the two challenges. We'll start with the first one. I think it's 10:30. I would propose to go forward unless I see hands raised, but I don't, in my screen at least, I don't see any. Sorry? Yes, I'm sorry. Yeah, I'm being reminded by my colleagues here that indeed, and I didn't say this in the beginning. So just to let you know, and I think it's in the program as well, so you should be aware. But we'll in all the three sections, so the intro, the first challenge, and the second challenge, we'll do a presentation, a short one to set the scene. But ECHA will do a presentation as well from ECHA's point of view to set the scene. So we'll do that in the next ones to come, but we'll do that definitely in this one too. So I'm terribly sorry, Christelle, to overlook that, but I'll give the floor to you. I'll see if I can. Let's see how we can do that. So if you could turn on your mic and your camera, we should be able to see you. I will turn off mine just in case. Yes, we can see you. So if you can unmute, I'll mute my mic and you're good to go. Thanks. I'll click the presentation.
Thanks, Hans. And I will try to be quick to go through the different slides. But thanks for also giving us the chance to bring few slides to set the scene from authorities' perspective. So this is a presentation that has been prepared in ECHA, but I see also that here today there are quite a few colleagues from Commission and Member State, and I hope the presentation also reflects the work we have been doing in the PETCO working group. So next slide, please. So first, we thought it would be important to really set the scene and to explain again why we need to progress on those substances. And very briefly, a reminder on the aims of REACH, ensuring a high level of protection of human health and the environment from both authorities, but also from industry perspective, promote alternative to animal testing, ensures the free circulation of substances on the internal market, and enhance competitiveness and innovation. So we are still working into that context. I will also, in the next slide, go back a bit to the history and how we have started to focus even more on the petroleum substances from an authority perspective. And as you know, it came with the SVHC roadmap to 2020, where we had this goal to have all relevant currently known SVHC included in the candidate list. And there were in particular in this roadmap some highlights on the petroleum substances. I see that the presentation has some issues, but I hope you will see everything once you receive the slide. But now in 2020, what you cannot see is the reference to the chemical strategy for sustainability. No, I think it was the closure of the SVHC roadmap. Sorry, yeah, I need to remember what I had in those slides. So we have put forward a short document to close the SVHC roadmap, where we have highlighted what has been done, what are the main achievements, and what we flag in there is that actually the Petco works was not finalized and need to be continued under the integrated regulatory strategy. Next slide, please. Yes, and to put even more the work into perspective, and I see that most probably all my links will be blank on the slides. In 2020, there's been Commission communication on the chemical strategy for sustainability in October 2020. In there, we have few objectives. Among those are the better protection of citizens and the environment, which in particular includes increased protection against most harmful chemicals, such as the extension of generic risk management approach to ensure consumer products do not contain CMR, PBT, ED substances, for instance. And also the idea that we would extend those to professional uses and potentially other hazards. There is also in this communication the need to continue to boost innovation for safe and sustainable chemicals. Why I've put this here in those slides is because of the reference to consumer and professional uses having CMR PPT properties. And you mentioned, Hans, in your presentation that only 2% of the petroleum substances, the volume of petroleum substances goes to widespread uses. But looking at the overall tonnage, this is quite a lot for us as authorities. And there is really now this strong push to avoid having any of those substances in consumer and professional uses. So I'll come back to that later as well. Next slide, please. Then from SVHC roadmap to integrated regulatory strategies, in there you may know that we have few aims, and one is actually to efficiently select group of substances that raise potential concern, and of course the petroleum are among those. Generate information needed to assess their safety so that any remaining concern can be addressed through the most suitable regulatory risk management measures as soon as possible. We have really this urgency to act on those group of substances. We have also the need to ensure appropriate and timely intervention by all actors, being ECHA, member state, the European Commission and industry, and also to provide confidence among stakeholders that actually registrants meet REACH information requirement, promoting improved communication on safe use in the supply chain. Next slide, please. This is just a scheme that introduces the integrated regulatory strategies and how all actually REACH and to some extent CLP processes are integrated with each other. And what we are doing on all groups is what you have in the center, is assessing the regulatory needs. So assessing whether actually those group of substances would merit regulatory risk management. So this is really the core of our work. Next slide, please. Targets. So what do we aim at under this integrated regulatory strategy is to conclude by 2027, which is not so far away, on all registered substances, on whether they are of priority for EU-level regulatory risk management, being authorization, restriction, or maybe action under other legislation, or whether they are actually currently of low priority for further EU-level regulatory action, because we conclude that they are of low hazard, or because for the time being, based on the uses, for instance, registered, we believe we don't need to act for the time being. And this, of course, can be revisited. And of course, those targets are also in line with REACH Evaluation Joint Action Plan. Next slide, please. So how do we follow this work under the IRS is via the chemical universe mapping that you can find also on our website. So this is the current view we have on our website, where we are in mapping all those substances. And this has been published earlier this year, and we are updating this on a yearly basis. If you click, please. For your information, where are the PETCO substances? For the time being, they are under this pool of substances under data generation. So what it means is that we are still thinking, and they are actually under assessment still thinking what kind of data are needed before we are able to conclude and which data to generate. But the aim by 2027 is also for those substances to some extent that they are moved to the green boxes. And maybe you can click a second time, because this is what is our target about. So that we have by 2027 identified whether some of those substances would merit regulatory risk management action, or whether we would conclude there is no need currently to have any action. Next slide, please. Then we have put few slides on some of our concern regarding those substances. And the first one is about the composition, which most probably will come up also in the discussion today. So the substance identity profile, it describes the composition and manufacturing processes for UVCB that are covered by the data that is jointly submitted. We have also the notion of boundary composition, which refers to the technical reporting in Euclid dossier of all the composition of the substance covered by the registration. From our side, two message. Boundary composition was not designed as a tool for only sameness assessment. We really link it to the level of detail that should be available and linked to the hazard assessment purposes. And this level of detail is most probably different from the level of detail needed for the substance identity purposes. So most probably we will come back to this level of information needed at the composition level, but this is something that is really important for us as authorities. Variability in composition could be accommodated in terms of SID, especially for process-defined UVCBs, but this is very challenging for hazard assessment and for proposing later on some regulatory action on those substances where needed. But we will come back to that. Next slide, please. On the hazard, as said, because of the nature of the product, we have suspicion for CMR and PBT properties. And we know that some substances contain some of those CMR constituent or PBT properties, but for many other being constituent or block, we have actually suspicion. And this is what worries us as authorities. Saying that, we also acknowledge that assessing those properties for those substances is challenging. And maybe I go quick on that, but because Hans already flagged many of those challenges, and we will come back later to that. Next slide, please. From the exposure side, we had some initial focus on prioritization of substances based on use. So we have clarified quite a lot about the uses of those substances. We focused, as said, on consumer and professional uses, which are the highest priority. We also gave lower priority to those industrial uses and intermediate and fuel only. Saying that, we have also flagged as authorities that we have some concern about the migration of constituents through the supply chain, as we see that some of those constituents of concern are actually moved through the supply chain and will lead to some concern from our side and question on how to regulate again. Next slide, please. Then some also challenges from regulatory risk management, just also to keep in perspective that, of course, today's discussion will focus a lot on challenges related to hazard assessment to some extent, but I thought it would be useful also to put it in perspective. We need this information because we want to understand how to regulate those substances. And I think this applies to us as authorities, whether we want to bring some of those for some EU action, but also from your perspective as industry when you look at your risk assessment and ensuring safe use of those substances. So what are the challenges there? What we need before we regulate a substance is actually to have this confirmation of the hazard properties. So we need to understand the hazard. And this is very challenging for the petroleum. And two ways to do that is having harmonized classification of substance, constituent, block, or candidate listing for properties like PBT or EDs. For that, we need meaningful hazard information so that this supports further regulatory risk management. And maybe later on we can come back what we mean with meaningful, maybe in the discussion. I'm sure we will also come back to what do we need, being constituent versus whole substance. And again, we acknowledge from that we cannot know each individual constituent of those substances, which means that we need to find some maybe compromised way to handle those substances, as also the whole substance will not necessarily answer our needs from regulatory risk management. The high variability in composition means that actually same substance may have different hazard. I think in your presentation, Hans, you mentioned that within one category, you should have quite some similarity of the substances. But of course, from authorities, we focus also within one substances. Sometimes the presence of only one constituent above regulatory threshold makes it different and means that we need to regulate differently. So for us, the question is really how to regulate such substance in a proportionate and efficient manner. As of course, we don't want to impose very heavy regulatory risk management on the whole substances, if in the end it's only for one member, one registrant where we see that there is a single constituent above threshold. Next is the level of unknown, which also brings a lot of uncertainties for us as authorities, but I guess also for you in industry. And it's there for us the question around uncertainties and what can we accept from both sides to ensure and focus on safe use of chemicals. Next slide, please. So we have progressed as part of the PETCO work since we started. So as said, we have more information now on use. So we have some clarity, but still question, for instance, those intermediates. There has been quite a lot of work also on this analytical analytical work, so we have a better understanding of the chemistry of the substances. For the human health, additional testing proposals have been submitted, and for environment, we have some agreement that the block approach is a good pragmatic starting point. But saying that, next slide, please. We still have quite some work ahead of us, and hopefully today also help to progress. As said, we have quite some information on uses, but really this information needs to be maintained. So you need to have a close look at your registration dossier and update so that we have clarity on the uses and they represent the current uses on the market. And of course, the concern about the migration through the supply chain is a real one for authorities. On the analytics, so we have enhanced our understanding, but we really need some more work, especially to ensure optimal testing and solid implementation of the block approach and to substantiate read across. On human health, we have additional testing proposal, but still quite some categories and substances to work through. So this is a good start, but we need to continue and plan this work so that we progress. For environment, we have the block approach, but it has not been without any difficulty that we have continued our discussion on that. You know that some chemicals should already be handled as PBT because of the known PBT constituent they contain. We really see that the number of higher tier studies is insufficient there, and there we need to discuss what is the testing strategy. And we have discussion ongoing, what to test, constituent, block. So, and hopefully today the discussion will help also on that. Next slide, please. Few words on sustainability also because this is quite present in this chemical strategy. So your substances are under attention. As said, from our perspective as authorities, we need to take action because they contain CMR and PBT properties. So there is really willingness from authorities to take action. And now we have also this focus not only on consumer, but also on the professional, which applies to your substances. They are difficult to assess complex and variable chemistry and properties. That's one thing that we acknowledge, but the database also needs to be expanded, particularly because they are complex and variable and difficult to assess. We need to have more data to support read across, to support the block approach. And of course, this work is also relevant in the future. We had some discussion on that with you. Although virgin fossil sourcing for fuels as an end, it may be that some substitutes will have actually the same similar challenges. So anything we do now will help for future substances as well. In addition, the current chemistry will continue to be used in other applications, and this actually covers some of the uses we may be worried about already currently. And other uses might be developed. So overall, we really need to invest some time in this work also to learn for the future, and it will help us to design better chemicals for the future. Next slide, please. So all this, I think, really call for collaboration. That's what we have seen in the past. We need to discuss and have a constructive approach on that together. And hopefully this workshop today also will support this. Thanks.
Thank you very much, Christelle. Thanks for giving an overview. Indeed. So in terms of time, I think I don't see any hands raised at the moment. I would suggest that, after these two introductory presentations, we move on and we keep the discussion that we foresee for after the next challenge. So indeed, as you ended, I think there's a lot of information needed, like you said. I mean, data directly to fill our dossiers, but also a lot of information needed to support the approaches that we are developing. And that needs to be integrated all together into a testing strategy, both on the health side, but also on the environmental side. So these are the two main topics that we'll discuss, and we'll start off with the first one on human health. So I envisioned this one to start now until a 1:45, after which we have a break. Let's see how it goes. We have first two presentations. So first the Concavity presentation, and after that a presentation by ECHA given by David Bell. We can see maybe at that stage best if after those presentations we say we need a short break before we start discussing, or we dive into the discussion. We'll see how it goes timing-wise. But we'll start with the Concavity presentation. This is going to be covered by Jean-Philippe Chenard first, who is the Science Executive for Health here at Concawe. Carol will again touch upon the analytical aspects of it, and I will cover a little bit on the some detail on the in vitro approaches and our testing strategy. But please, Jean-Philippe, to you first.
Thank you. Good morning, everyone. So I simply to start with repeat the challenge we have. So we are committed to. You understand we are really committed to deliver the testing, the required testing program. And for that, we need to overcome the practical challenges of petroleum UVCB substances, such as taking animal welfare and deliver the information in the acceptable time frame, I understand, then by 2027. So to tackle this challenge, we really propose that a combination of animal testing with other alternative in vitro method underpin the similarity and read across. So for practical reason and to understand the reasoning, we can subdivide that in four steps. First, the chemical similarity, understand the chemistry. Then you have the biological information input, both in vitro and in vivo. Then, as in a discussion in an article, you integrate all that to understand really detail the understanding you have from the data you have collected above. You can also build hypotheses, read across hypotheses, and then you have really the confirmation of the sample you need to test. You test them. So another way of showing that, Hans, please, is well, just exactly the same, but with the four steps and the stake. So first we have the hydrocarbon space, so the chemical space, describe it, have the boundaries, as you said, Christelle. So that's the chemical information. Then we can add on that all the biological information, the in vitro studies, such as the CATAP program, the short-term toxicity study, OECD 422s. We integrate all that, and step 4, we generate the data. So Carol is much better placed than me to explain you the first step. So Carol, if I can give you the word for the step 1. Thank you.
Thank you, Jean-Philippe. So yes, to present the approach to describe the hydrocarbon space of a petroleum substance, I'm going to start with an example with the gas oils. This is where we have developed this approach of hydrocarbon space mapping. So by gas oils, I'm referring to 3 categories of substances. So this is the vacuum gas oils, hydrocracked gas oils, and distillate fuels. That's one category. The straight run gas oils and the other gas oils, and together these make up 15 substances that are currently in active registration. So in order to map the hydrocarbon space, we need to have multiple samples per substance, and these are collected from registrants in volumes that we can fulfill both the analytical characterization but also eventual animal studies. So in total, we gathered 129 samples across these 15 substances. The analytical characterization, including quantitation of the 3 to 7 plus ring polycyclic aromatic carbon constituents, was using a combination of DMSO extraction of the substance followed by gas chromatography mass spectrometry. This is the PAC2 method. The data from this method was validated using HPLC, again quantifying the total mono, di, and tri-plus aromatics. In addition to this, we looked at, with GCMS, the quantitation of 32 EPA and GRIMA polyaromatic hydrocarbons. But the focus of the hydrocarbon mapping was the two-dimensional gas chromatography analysis. And this analysis, GCGC, separates and quantifies constituents of the petroleum substances based on carbon number, on volatility, and then on hydrocarbon class, the polarity, where we can divide into subgroups of paraphenics, naphthenics, and aromatics classes. So on the next slide, we can see an initial view of that two-dimensional gas chromatopic data. So by looking at the 4 groups of hydrocarbon classes across all the carbon numbers, you can see that the 129 samples across the 3 categories are clustered together. And there's no difference between each of the 3 gas oil categories shown in the different colours. There are a few outliers, but these are not related to any particular category. And therefore, the gas oil samples from the 3 categories appear to occupy the same hydrocarbon space. Now, on the next slide, we look at this space in a little bit more detail. We have 4 blocks here, and let's just refer to one block as a sample. Let's take the one on the far right. We want to take a closer look at the measured concentrations of constituents per sample, and we developed this map whereby on the y-axis you see the carbon number, and on the x-axis you see the hydrocarbon class, starting with normal paraffins and moving over to tetraaromatics on the x-axis there. So within each cell, which we call a hydrocarbon identifier, we have the measured concentration of that constituent group in a sample, and that is normalized to the full range of the measured concentrations of the same hydrocarbon identifier in all the samples. So the greater values are in darker green cells, and they represent the highest concentrations of the hydrocarbon identifier in the population, and the lowest concentrations are depicted in the yellow cells. So the comparative population can be all the samples within a category, in this case the other gas oils, or indeed you can take all samples across the 3 categories. So this is how we map the hydrocarbon space of each sample. The next step is to take a selection of samples from each substance, each of the 15 substances, to test for the OECD 422 bridging studies. And the aim is to select a sample of each substance that best represent the hydrocarbon space of the full category. So the samples are selected by comparing each unique hydrocarbon map with the data from other samples of the same substance, and selecting the sample combination with the highest minimum normalized concentration for a single hydrocarbon identifier. The 3 individual samples on the right side of the slide represent the samples selected for the other gas oil substances. And when this data is combined, we see this on the left side of the chart, we can see that the maximum normalized concentration across the 3 samples is expressed. And then we see a high proportion of the sample concentrations of each hydrocarbon identifier represented by the dark green cells. So when we look then at the lowest concentration of hydrocarbon identifier that was represented, and that is the carbon-19 normal paraphenics, where we have a 57% coverage, this still represents a greater concentration than measured in the majority of the other gas oil samples that were analysed. In this way, we can select test samples that best represent the full hydrocarbon space of the category. So when we repeat this exercise across the other 2 categories, we can then select 15 samples, 1 for each of the substances. So these 15 substances will be taken, these 15 samples will be taken forward to the OECD 422 bridging studies. And within these 15, we not only have a good coverage of the hydrocarbon space, we have also selected samples that have the highest level of 3+ ring PAC constituents per category. It's because, and we have focused on these substances, or these samples, because it's these constituents, these 3+ ring PACs constituents, that we believe are driving the hazard effects. What we've also done when selecting these 15 samples is look ahead to provisionally identify in the orange blocks in the top 5 samples to propose for the next round of higher tier testing. And as these 5 samples represent not only a high coverage, as you see, of the 3 category hydrocarbon space, but these are also substances with high EU tonnage, so highest potential for exposure, and also the highest measured 3+ ring PAC constituent concentrations from each of the categories. So the final sample selection for the higher tier testing will be confirmed, of course, in the step 3 of the strategy, and that will be following the outcome of the OECD 422 and the biological activity studies, which will take place in the next step 2 of the strategy. And I pass back to Hans.
Yes, thanks, Carol. So indeed, what we're doing here is really working towards supporting this similarity, supporting the grouping, and we've now looked at that from an analytical perspective. So covering really the analytical, the analytical similarity. But now let's see if we can put a biological layer over that, so we can create this biological similarity as an additional layer to further start supporting our grouping of our substances and eventually the read across between them. So we first do this by adding an in vitro set of data. So we look into the in vitro biological space. We started at this stage, I think it's already 6 years ago, we started a project called CALAB with an international research consortium, different partners across the globe. I think we have our principal investigator, Even Russen, today on the phone as well, if I'm correct. I'm trying to see in the list, but it's he should normally join us as well for the discussion. And of course, all the people who have participated in this from Concawe and our member company side. You see an overview of the program here, the different work packages we had. And there's a nice infographic produced by our comms team on, the quite large amount of data that we have generated throughout the years in this program. I'd like to refer to the Concawe website, concawe.eu/CALAB, where you can find a lot more detail on this program, as well as all the peer-reviewed publications we have published so far. They are open access. There's also a project report there for your information. And there will be more, there are more papers in the pipeline which will be published there as well. So today we'll take you just through, using an example, we'll try to explain what we have done in CALAB. So we have tested multiple cell types and a lot of assays in these cell types as in vitro screening tools. So we had induced pluripotent stem cell derived tissues, and we had the more common cancer-related cell lines. So what you see on the left side here is the different cell types that we have used. I'm sorry, it only includes the acronyms. I think the half of them has dropped off, but this it illustrates the point. So the first ones are, for example, cardiomyocyte cells. So these are heart cells, endothelia, liver cells, etc., going down. So we have all different types of relevant cell lines tested. So we have exposed our cell lines to petroleum substances and actually to extracts of petroleum substances, because as you can imagine, petroleum substances are lipophilic. They don't like to go in these in vitro assays. So we have to take the biological relevant part out, and these extracts are indeed, you're able to expose the in vitro assays with those extracts. So we know that they will end up in the test medium. So we tested these substances, and what you see there on the left side is a pie approach, the ToxPie approach. It's a published methodology that we have applied. And each piece of the pie is a different type of data. So a different cell type and different assay types that we have measured in these cells. Now we can make these ToxPies for each and every substance that we tested. So we have tested the whole range of petroleum substances. And what you see now in the middle panel is two example categories. So there's your heavy fuel oils, marine fuels type of products, and waxes on the right side. And you can immediately see from a high level perspective that within those categories, the tox bias, so the biological responses are similar, not the same, but similar. And they are different, very different between them. So you see a lot more response in the heavy fuel oils than you see in the waxes. Again, this is just one example. All the data is described in the Concavity report. You see it referenced on the right side. And we have a peer-reviewed publication on all of this work, the bioactivity screening as well out there in LTEX, House et al. 2021. So published beginning of this year. So now, of course, the question is what drives these different responses? And the hypothesis here is that it's driven by the constituents we believe are linked to the toxicity or to the biological effects, and these are the PEHs, and we'll get to that in the next section. Now, this is just again an example of the data. Many more in vitro data going into this, but it's still only in vitro data. We know that this is not sufficient. There needs to be better confidence in these data, and we start doing that by adding a layer of in vivo data on top of that. So to increase the confidence in the similarity between substances, we have started a program on OECD 42 bridging studies. So that's the next layer of data. I'm using also here the example of the gas oils that Carol just talked about. So the OGOs, the straight run gas oils, the SRGOs, and the VAGOs, the vacuum and hydrotreated gas oils. As Carol said, we will test one sample per gas number per substance in each of these categories. So that makes 15 samples in total. So these will be 50 OECD 42 bridging studies. We will also add 6 additional ones to test them in a different exposure route. So the 15 studies will be done by oral exposure, but from a risk perspective, from an exposure perspective, real life exposure, of course, is 2 different exposure routes, more on the dermal side, inhalation side. But so we add 6 additional dermal studies as well, which gives us the benefit to start comparing exposure routes and hopefully generate supporting data to do route-to-route extrapolation for risk assessments. The oral data will help us to compare toxicities across these substances, across these categories, or across that full chemical space of those 3 categories, and hopefully add that layer of similarity from an in vivo perspective on that chemical space. Of course, we will screen for repeated dose and reproductive toxicity endpoints as well, which help us plan for the higher tier studies on the longer run or on the next step. And it will help us to confirm the sample selection for those studies. But also, we can use these studies in a smart way to minimize animal testing. If we can extend a couple of those studies, we can use them as rangefinders for the extended 1 generation studies and the higher tier testing. Another big opportunity of doing all this animal testing work, not only for this one, but also for the higher tier testing to come, is that we have an opportunity now to save tissues and to further develop our in vitro methodologies or in vitro screening assays with taking samples from in vivo studies and comparing them to the in vitro assays that we have. So one-to-one anchoring between in vivo and in vitro new approach methodologies. And I think with that, we have added that biological similarity layer in step 2. So we now have, at this stage, the analytical data to add an analytical layer, analytical similarity on this hydrocarbon space. We have a biological layer in terms of in vitro data as well as in vivo data to be generated this year. So now all of that data integrated together in step 3 will hopefully give us a nice, what we call chemical biological similarity principle to support the grouping. So we can see if the substances within that chemical space are similar in both the analytical and biological dimension taken together. Now, as I said in that example for CADAP, when I showed the tox bias for the HFOs and the waxes, we said that these are the major differences in these effects are probably linked to the hydrocarbon constituents in them, so more specifically the pHs in them. So that's the first thing we tested. And this is, again, an example from CADAP. And here you see a very nice trend in the chemical biological space. So this illustrates what I mean with that. So if you see on the horizontal axis, the x-axis, it's the pH content. So it's the 3 to 7 ring pHs. On the y-axis is the bioactivity profiles of all the substances. So you can see in that cloud a very nice trend. If you go higher into the concentration of pHs, you see a higher biological response, an increased biological response. On the right panel, you see the different categories separated out. And you can see again, you know, if I put the HFOs, I'm sorry for the silly descriptions, but it proves the point. You have the HFOs, the marine fuels, they're a very nice trend. We know that some of these contain a low level of pHs, and you see a low biological response, and some of them contain a high level of pHs, and they have high biological response there. So you see a nice trend. For the waxes, we know that they don't contain, or a very low level of these constituents, and low to zero. And you see all the biological responses, all the substances really lumped there together in the bottom left corner of the graph. So almost no biological response. So there's a strong correlation between the pH levels and the biological response there. And that helps us to build read-across hypotheses. Now, this is not sufficient. To build a thorough read-across hypothesis, you need a predictive aspect in that analysis as well. And we can do that with other types of in vitro data and programs that we have running. So I'll give you one example from a project we have conducted, and some work is still ongoing, together with the University of Wageningen. So what we did here is, and this is an example for mouse embryonic stem cell, we used different types of in vitro DevTox, developmental toxicity screening assays. And the results here are for the mouse embryonic stem cell test. So for those who are not so familiar with it, from a, very simplistically stated, you have stem cells, and we differentiate them into heart cells, into beating cardiomyocytes. So that differentiation from a stem cell to a cardiomyocyte is measured. Now you see graphs here. If you see a nice horizontal graph, it means you have nice growth of the cells and you have no cytotoxicity. You see two major graphs there. So one is for cytotoxicity and one is for the differentiation of the cells. If you now first look at the first category of substances that we exposed, and these are base oils, which are very highly refined. They don't contain any pHs. No aromatics, no 3 to 7 ring pHs. And you see that you have no cytotoxicity, so the cells remain viable, they remain alive, and they grow nicely. They nicely differentiate from stem cells into heart cells. Now, if you expose them to extracts of pHs, so distillate aromatic extracts and residual aromatic extracts, you see the cells are not killed. They grow nicely, the top horizontal line, but you see a strong effect on the differentiation of those cells. So the development of the cells from stem cells into heart cells is impaired. Now, if we expose them to diesel type products, which may contain some pHs in some examples, but more moderate, so not a high level, you also see an effect. The cells remain alive, but the effect on the differentiation is less pronounced. You see a different type of the curve, and you see the effect later in the at a higher concentration. So there's a very nice concentration-dependent effect here on the development of these cells. So that effect observed is indeed strongly correlated with a 3 to 7 ring pH content, which supports our hypothesis further. And it also is strongly correlated with in vivo data. So where we have in vivo data on these substances, DevTox data, there's a nice correlation between what we see in vitro and what we have observed in vivo. So this helps us to build these read-across hypotheses and to integrate that with all the other types of data in a weight of evidence to support our an integrated testing strategy. And that leads us into step 4. And I'll pass over to Jean-Philippe here so he can close the presentation on
So just the summary, after all the information you've received. So you see on the first step, we collect all the information on the chemical space with the techniques that Carol explained you. We have in vitro profile data available. We are just committing the OECD 422 toxicity test. So just for your information, the test material has been shipped shipped to the lab, and the test will actually start very soon. So we have quite a database that we need to understand, integrate, and so on. So all that will allow us to test and to select, confirm the sample we would select for higher tier testing. So we have already a proposal based on the chemical information we have. So let's name them sample 1, sample 2, 3, 4, and 5. And so we will perform the high tier test, so prenatal development test and extended 1 gen. So the next slide is so exactly the same. So we will, step 4 is very short, not a lot of discussion. It's just doing and delivering the test. Of course, we need to develop the step 3, integrate all the data we have, develop the testing proposal, and have the ECHA decision. So I think with that, so the discussion, well, there will be an ECHA presentation, but maybe let me propose some statement to start the discussion, brainstorming. So we believe, we propose that a holistic approach addressing the full hydrocarbon space as described, as we've just described, overcome the practical challenge of a substance by substance approach. But we need to be sure of that approach. So which improvement could increase the confidence and obviously then decrease the remaining uncertainties in the proposed chemical biological similarity assessment? Does also the holistic approach facilitate inter-category read across? We have data. Let's use it as well. Huh? So we need to facilitate read across from all what we have as an information on petroleum substance. And we propose also that UVCB tailored guidance on information requirement regarding similarity grouping and read across would help the regulatory assessment of the substance and the REACH and in due time. Thank you.
Yeah, thanks, Jean-Philippe. So I think so we'll pull that slide back up when we start the discussion as a discussion starter. I'm realizing I'm not using my camera. There we go. So I think with this, it closes our part of the presentation. I see that David, you're online. Welcome. Thanks for joining. Hey, I'll give you the floor. Let's see. I'll scroll through the presentation, and you just tell me when to click. There you go, Dave.
Thanks very much, Hans. Yeah, so I'm going to give a short summary of our thoughts from the human health side and the challenges for petroleum UVCB substances. So can I go to the next slide, please? I'm following a fantastic presentation with lots and lots of data from Concawe, but I just want to make clear here that the presentation that I'm giving does not present a formal view of ECHA and the compliance of any substance, nor is it specifically aimed at the presentation we've just heard. This is a more general level. This presentation is informal and it's not intended to present a definitive view. And if you want to get a definitive view, then you should consult the ECHA guidance and website for definitive advice. Next slide, please. So Christelle put the point very clearly that we have concern for petroleum substances. There's all sorts of possibilities of CMR properties for these substances. So we need to have information on these substances. This is the point of REACH. And an underlying principle with REACH is no data, no market. So it's a major ECHA goal at the moment, and not just ECHA, but the Commission, the Parliament, to make sure that dossiers have good information, reliable information that tells us about the properties of substances. That's what we want. There is an opportunity from the registrant side when they provide that information to maximize the benefit out of getting that information so that you get data which is highly reliable for your purposes and enables you to deal with chemicals safely and yet it does so in a sensible way that meets your needs. So there's considerable potential for everyone here to benefit. Next slide. As the name suggests, UVCBs, unknown variable. It's a nightmare. How do you account for hazardous properties associated with unknown or variable composition? There are real technical problems associated with this. Additionally, as well as just dealing with the straightforward idea that if I have a UVCB, how do I tell whether or not I'm generating information which is enough for this one substance? Frequently, people want to use adaptations and principally grouping and read across. And in order to do grouping and read across, one of the things that you need to demonstrate, including for UVCBs, is structural similarity, because read across in reach requires a demonstration of structural similarity. Now, in order to make a demonstration of structural similarity that is going to be able to impact or underpin toxicological or ecotoxicological properties, that really means that you need to have detailed information on the constituents of your UVCP. So, and just to outline a theme, for substances, a certain amount of compositional information is needed to demonstrate substance identity. However, if you're trying to demonstrate that you have sufficient structural similarity for the purpose of read across, you may need much more information, much more compositional information than is required than just for the purposes of substance identity. As well as having, if you want to do grouping and read across, not only do you need to be able to show structural similarity, but you need to have a basis for predicting the properties of substances within your category. That will be case specific. The particular circumstance of the case will bring different hypotheses and different data requirements. But in every case, you need to be able to justify why you can make a prediction of properties. So these are the basics. Next slide. What I'm giving here is that an example of a generic approach which can be applied to a big category. So if you have a big category of UVCBs, it isn't hopeless. There are ways forward. Some of them will be absolutely case specific, but others you can try a more generic approach. You need to have that structural similarity to be able to predict similar properties. So you need to have comprehensive information on composition. But you also need to have substantial information on the properties. That can be in vivo tests, but it can also be in vitro tests and mechanistic tests. But it will depend very much on the nature of the particular category, the particular chemicals that are involved in your read across hypothesis. Additionally, there's a need from ECHA's side that we deal with this at the level where you are providing testing proposals to make the higher tier tests, the tests in Annex 9 and 10, which is to say the 90-day, the first species PNDT, the second species PNDT, the extended one generation reproductive toxicity test, and any in vivo mutagenicity tests that are required. Key issue here, so this sort of generic approach is possible, and it can be applied to many UVCBs, or many categories of UVCBs, I should say. But note the requirement for information. If you do not have information that is necessary, the read across will not work. It will be rejected. If you have insufficiency of supporting information, it can invalidate the read across, or it can lead to a great increase in the amount of higher tier testing that is required to substantiate the read across. And at a fundamental level, if you can't provide information on composition, you simply can't have the read across because that's a legal requirement for read across. Next slide. This is a little bit of information hot off the press. The Commission has approved changes to the legal text for grouping and read across, and these have been approved by the Commission, and I understand that they are imminently to be put into the official journal, and they will have legal effect from mid-July, and they will have force from, so you'll have to abide by them from somewhere in January 2022. And this is from the text for grouping and read across. Basically, this is the future test that will be applied. The structural similarity for UVCB substances shall be established on the basis of similarities in the structure of the constituents. We recognize that in some cases that it isn't technically possible or impractical. You still need to be able to demonstrate structural similarity to enable a quantitative and qualitative comparison of the actual composition between the substances. So this is future law that will come into force, that will have effect from next year, effectively. Next slide. And so I just want to finish that with a kind of generic theme. There's what ECHA can do, and there's what registrants can do. And our jobs are different. When ECHA gets a dossier, we have to check for compliance, and we can see if all the necessary information, the standard information requirements, are being provided. And if it hasn't been provided, it's very simple for us. We simply request all the missing information. We don't ask for adaptations. We don't ask for something to be made a little bit better. We just look at a whole category. We say, what's missing? And then we say, everything we want. We just want all the tests. It's different in the case of testing proposal evaluation. In a testing proposal evaluation where you have submitted testing proposals, ECHA can take account of testing strategies, for example, with read across in a category. Within a testing strategy, you can be proposing to do the higher tier tests, 90 days, PNDTs, but you can also propose that you will do other tests. That can be analytical chemistry, it can be lower tier tests, it can be mechanistic work, which will support that. And we have to take a view on the testing strategy rather than just the single tests, the individual tests proposed. So that's a major difference between compliance check and testing proposal evaluation. So those are our tools and those are our options. But the point I make is that you as registrants have the ability to propose adaptations. We don't. You can propose testing strategies. So you really have a large input in the type of decision that ECHA will make. If there are data gaps at compliance, we simply ask for everything. You have the option when you're addressing data gaps to generate information, to start producing data and to make a testing strategy which can be more efficient. But it's a matter for you to address, and it's not something that ECHA can do. And that's your opportunity to really contribute to the process. I think that's the end of my presentation, and I thank you for your attention.
Thank you very much, David. Let me put my camera back on. There we go. So I think we